Welcome to your Unit 8 guided practice. So starting with our mole ratio, it says write 2 mole ratios for the hydrolysis of water. So we need a balanced chemical equation here. So therefore we look and we see that there's 2 hydrogens, 2 hydrogens. Those are balanced. 1 oxygen, 2 oxygens. So not balanced. So we put a 2 here to balance it. But it also means now we have 4 hydrogens. So we got to come over here and balance that. Now that we have a balanced chemical equation, we can say that we have 2 moles of water to every 2 moles of hydrogen. We can also say we have 2 moles of water to every 1 mole of oxygen. Okay, looking at our next one, it says write 2 mole ratios for the decomposition of calcium carbonate. We look and we see that it's already balanced. So here, all the coefficients are 1. So meaning we have a 1 mole of calcium carbonate to every 1 mole of carbon dioxide, 1 mole of calcium carbonate to every 1 mole of calcium oxide. And remember, we can also say we have 1 mole of carbon dioxide for every 1 mole of calcium oxide. And then the last one, this one's a little bit harder because it's harder to balance. I'll give you the balance equation, 2, 25, 16, and 18. Go ahead and see if you can figure out how I balance that. And then it's just, we can say we have a 2 to 25 ratio, a 2 to 16 ratio, a 25 to 18 ratio when we're talking about those guys. Moving on to some stoichiometry. So when we're looking at stoichiometry, it says calculate the mass of oxygen produced when 200 grams of water goes under electrolysis. So there's our equation way up there. So all we're going to do is start with anytime it says grams of water, we need the molar mass of water. And we know that 1 mole of water equals 18.02 grams of water, and we also want the mass of oxygen. So when you look up here, we have 2 oxygen atoms, and so 16 plus 16 is 32. So now I know that I have 1 mole of oxygen equals 32 grams of oxygen, and this is my water. We'll make that blue. So we know that it's water. And then lastly, we need a mole ratio between these two guys. So oxygen and water, we have a 1 to 2 ratio. So meaning we have 2 moles of our good old water for every 1 mole of oxygen. Okay, we're going to take these guys and we're going to plug these guys into our dimensional analysis. We'll shrink them a little bit so we know what we're working with. And we say that we're starting with 200 grams. 200 grams of water. So we start 200 grams of water. The only thing that says grams of water is right here. So we put that part on the bottom. We put the other half of the conversion factor on top, which is moles of water. Now we put moles of water on the bottom because we got to keep going with our conversion. And put the other half on top, which is moles of oxygen. And then lastly, since we're not done with our conversion factors and we haven't gotten to mass of oxygen, we keep going. We put moles of O2 on the bottom and grams of O2 on the top. And we see that we have our dimensional analysis set up, and then we just multiply the top, divide by the bottom, and we will get an answer of 177.6 grams. Okay, moving on to our next one. Some hints here. On this one, realize that you are dealing with the calcium oxide, which is in the very top up here. So you have a 1 to 1 to 1 mole ratio. You're going to need the molar mass of calcium oxide. You're going to need the molar mass of calcium carbonate. Make sure you write the 2 molar mass conversion factors, the mole ratio conversion factor. Start with your 180 grams and see if you can't get the answer there. This last one's kind of tricky. It wants the volume of water, and it's the same reaction that we used right here. So there's our mole ratio. The only difference is that you want volume of water, so you're going to have the mole ratio between oxygen, between octane and water, and then you're going to have the molar mass of octane, and you're going to have this conversion factor of 1 mole of H2O is 22.4 liters of H2O. Now you should get an answer of 353.7 liters for your answers. See if you get that. Moving on to limiting reactant, it says what mass of iron 2 chloride is produced when 50 grams of iron reacts with 30 grams of chlorine gas. So first thing we need anytime we're working in stoichiometry is we need a balanced chemical equation. So this is iron, which is Fe, reacting with chlorine, which chlorine is a part of Brinkelhoff, so it's Cl2, and it produces iron 2 chloride, which is FeCl2. Okay, there's our chemical equation. It's already balanced, so all of our coefficients are 1. So when we're doing this, we're going to go ahead and you can either convert to a product or convert to a reactant, meaning you have 50 grams of iron, and we convert it to moles of reactions. So in this, we convert it to moles, which 1 mole of iron is 55.85 grams of iron. And so it's 1 mole. And then within one reaction, you have 1 mole. So what's the coefficient in front of iron? 1. So 1 mole of iron in 1 reaction. And so when we do this, we can produce 0.9 reactions from that iron. So now we have to compare it to our 30 grams of chlorine. So we do the same thing. 30 grams of chlorine, which is Cl2, set it up. It is going to be 70.9 grams per mole. Not 79, but 70.9 grams per 1 mole. And if we look at it within one reaction, how many chlorines do you have? How many chlorine? What's your coefficient? 1. So all you do is you set it up, 1 chlorine for every 1 reaction. So when we do this, we get 0.42 reactions, and that means that it produces the least amount, which means that is the limiting reactant. So on B, I'll give you a little bit of hints when we're looking at B. When we're doing this one, you have 500 grams of nitrogen gas is mixed with 1.2 kilograms of hydrogen gas to produce ammonia. I'll give you the chemical reaction. So it's just going to be 3H2 plus N2 produces R2NH3. There's our reaction. Now you're going to do the same thing we did above. One of the tricks right here is this is kilograms, meaning it's 1,200 grams. So 1,200 grams of hydrogen. Do the same thing that we did above and see if you can figure out what the limiting reactant is. And then lastly, for this one, we're starting with making it a little bit easier. We're only doing moles here. So you don't have to convert to moles. It's already in moles. So just look at how many reactions can come from that. Your balanced chemical equation for this is going to be 2Fe plus 3O2 produces Fe2O3. Okay? And what you should get for your answer is that O2 is the limiting reactant. Go ahead and try that out and see if you can get that one. Now looking at percent yield. Now percent yield, we use an equation that it's our actual divided by theoretical times 100, and it's going to give us the percent yield. So on our very first one that we're going to do, remember we have to start with a balanced chemical reaction. So we have iron reacting with sulfuric acid to produce iron 3 sulfate and hydrogen gas. So let's start with a nice balanced chemical reaction. So we're starting with Fe, and this is 2 of them, plus 3H2SO4 produces 1Fe2SO3 and 3 hydrogen gases. So now we have a nice balanced chemical equation here to work with. We can go ahead and begin our problem. Now, since everything is dealing with our iron 3 sulfate, we're going to go ahead and convert everything to that iron 3 sulfate, meaning we're going to take this 50 grams of iron and that 100 grams of sulfuric acid and convert it to iron 3 sulfate. Because when it says the student recovers, what that means is this 80 grams of iron 3 sulfate is actually your actual yield. So in the equation of actual divided by theoretical times 100, that's going to be on top on the numerator, and then you're going to put your theoretical yield on the denominator. So we'll go ahead and start by converting that 50 grams of our iron to our iron 3 sulfate. Now when we look at it, we see that we have a 2-to-1 ratio, and so we're going to start with that conversion factor. So 2 moles of iron, so 2 moles of iron for every 1 mole of iron 3 sulfate. Okay. And then our other conversion factor, since we're starting with grams of iron and we're going to grams of iron 3 sulfate, and we know that we're going to grams because we have 80 grams of iron 3 sulfate. So when we divide those out, we need to divide them out in the same unit, so they both need to be in grams. So our next conversion factor is we need the molar mass of iron 3 sulfate and we need the molar mass of iron. So when we look at that, we go ahead and write that down. So 1 mole of iron is 55.85 grams of iron. And then 1 mole of our Fe2SO4 is, and it has a very large molar mass, so 399.7 grams of our iron 3 sulfate. Okay, so now that we both have our molar masses written down, we can go ahead and start our conversion. And so we're going to start with the number that we have of our iron. So we're going to start with our 50 grams of iron. We'll take these guys, make them a little bit smaller so we can use them. Okay, so let's start with our 50. So 50 grams of iron, and then all it is setting up our conversion. So we say, well, it's the only thing that said grams of iron. Well, it's going to be this guy right here. And so we're going to take that and put that on the bottom so that we cancel out that unit, and then put the other half on top. And then we're not 2 grams of our iron 3 sulfate, so we keep going. And next we're going to use our mole ratio because those units now match. And then put the other half on top. And we're still not to where we want to be, so we keep going. And now we have moles of iron 3 sulfate on the bottom, and then our 399.7 grams. Now this is going to give us a molar mass, or a percent yield, not a percent yield. It's going to give us a theoretical yield of 178.92 grams. Now we're going to take that answer and we're going to do the same thing but with sulfuric acid. Now you might be asking yourself, well, why are we doing the exact same thing with sulfuric acid? Well, it's because we don't know what the limiting reactant is. And so we can just go ahead and solve for the mass that each one of them would produce, and then the least amount is going to be your limiting reactant, and that's your true theoretical yield. So we're going to do the exact same thing, but we're going to do it with sulfuric acid. So the mole ratio between sulfuric acid and our iron 3 sulfate is 3:1. So we go ahead and we will write that down. So 3 moles of H2SO4 equals 1 mole of Fe2SO4 3. Okay, and then we also need the molar mass of our sulfuric acid. So 1 mole of our H2SO4 equals our 98 grams of H2SO4, and we've already found the molar mass of our iron 3 sulfate. So 1 mole, we need that again, Fe2SO4 3 equals 399 grams, 99.7 grams of Fe2SO4 3. Okay, so now we have our conversion factors. We can go ahead and convert these guys. So starting with what our problem gives us, it gives us 100 grams of sulfuric acid. So we'll go ahead and we will start with that. 100 grams of H2SO4. And then all we have to do is convert again. So we put our grams of H2SO4 on the bottom, 1 mole on the top, and then we keep going, and we put 3 moles, use our mole ratio, 3 moles of H2SO4, 1 mole of our iron 3 sulfate, and we're not done yet, so we keep going, and we have our 1 mole to our 397 grams, 99.7 grams on top. Multiply the top, divide by the bottom, and what I get is I get 135.95 grams of our iron 3 sulfate. So what that means is that we know that our sulfuric acid is our limiting reactant because it's the smaller amount. Well, what this also means is this 135.95 grams is going to be our theoretical yield. So what I do is I go actual, which is right here, so 80 divided by 135.95. Take that times 100, and that will give me a percent yield of my answer of 58.8%. And that's my answer to the problem. So pretty long problem, a couple steps you got to make sure you pay attention to, but that's how we do percent yield. So let's go ahead and move on to the next one. I'll give you a few hints. So on the next one, it says that a student mixes 5 moles of aluminum in excess oxygen. So there, it kind of cut some of the steps out because guess what? It already told you that aluminum is going to be your limiting reactant. So you don't have to do 2 conversions now. You just start with aluminum. And it says to produce aluminum oxide, the student recovers 120 grams of aluminum oxide. So he recovers this. So therefore that is your actual yield. And so now all you have to do is calculate the theoretical. You'll start with 5 moles and you will convert to aluminum oxide. And let me give you the equation so you can go ahead and try that one out. It's aluminum plus oxygen gas produces aluminum oxide. So go ahead and try that one. And then our last one, made really simple. It gave us our theoretical, it gave us our actual in there. And so you don't even have to do any of the stoichiometry. It's just dividing. And you should get 62.5%. See if you can get that one.